Welcome back everyone to another demo video. In this lesson, I will show you the characteristics of band stop and band pass filters from RLC circuits. What you got in front of you is the series RLC circuit. I have the values of the components for inductor, 100 millihenry, 4.7 nanofarads of capacitance, resistance of 2000, and I'll be putting in 10 volts output from the function generator. And here I've already set up my oscilloscope, and the reason why this blue is so fuzzy, it is because it's reading the voltage after the inductor and capacitor, hence it's measuring the voltage drop across the resistor. And because we have such low frequency, you can see that my voltage across my resistor is only 76-ish millivolts. And that's about 0.07 volts. It's almost nothing. Because we're trying to read such a small number, the oscilloscope can't really display in a setting where the other yellow line, for example, which is our source voltage, is reading 10 volts. The scale is way off. That's why it's showing that fuzziness, but that is going to get improved, our theory, as we increase the frequency. And when we hit the resonant frequency, then all of the current is going to go straight past the inductor and capacitor like a short circuit, and we'll get a maximum output for the voltage. Right, and that is going to get way better. And you can't really see right now, but I've also set up the math as well for calculating the drop between the capacitor and inductor. But because of all this craziness, you can't really see it. And I've also displayed the phasor angle as well. Right now we're showing between 114-ish degrees. But that phasor angle is going to get closer and closer. We'll be able to see that through this. Okay, let me lock the focus on my camera. And here we go. I want you to pay attention to frequency as well as the voltage for the resistance, because that's the output. So we're slowly going up. We're still very low. It's only 200 millivolts. It's only 0.3 volts. We're at 700 hertz. You can see that all the fuzziness is gone as we're getting close to getting 1 volt, not even. Let's continue. Okay, now we're at 1000 hertz. Still not much. My phase difference is still 80 something degrees. It got better from 110, 120, but still not as good. Oh, now that you can see that the phasor is down to 80 degrees, my amplitude for voltage of resistance is at 1 volt now. Perfect. Now I'm at 2 kilohertz. And I want you guys to see how that, okay, I may want to change my setting to go a bit faster. I'm at 3 kilohertz. And you can see that my amplitude for the resistance, which my output it went up significantly, correct? And oh, we're getting very close. Look at that. Right, I'm at 5,000, almost 6,000, and look at that, the shift, and look at the phase shift here, guys. Let's go back to 4, and then see it was about 60 degrees off between my source voltage and my output, which is the resistor voltage. And as I go closer to 6,000, and my phase has decreased significantly during that time. And it's only about 5 degrees. And right there, and I can't even get, it's only 2 degrees off. See if I can get super accurate. Look at that, guys. Look at that phase difference. We're reading like 1 degree, sometimes indicating 0, right? You can see that 0 at one time. There you go. I've stopped the operation that you guys can see. Here is my resonant frequency. Frequency 6.17 kilohertz, and amplitude of the source voltage is 8.93. Look at my amplitude for my output. My output is 8.43. There's only 0.5 volts difference between my source voltage, whatever I'm getting from the function generator, and um, the voltage that passed through the capacitor and inductor and ready to be dissipated across the resistor. It's same, right? So that at resonant frequency, we know that XL is equal to XC. They canceled each other out, leaving only the resistor voltage. Therefore, we are completely in phase with each other between source and the resistor voltage. And look at the blue, my math, right? It is almost nothing because source is 10 or 8.93, and my amplitude is my resistor voltage is 8.43. Well, the math should be almost 0. And as you can see, resonant frequency phase angle is 0. Now I'm going to move away from it by continuously increasing the frequency. I'm going to resume, and I'm going to continuously increase, and you can see that the blue is now moving away, right, from where it was before to it's moving away now. Because as the frequency increases, in inductance reactance increases, therefore I'm starting to move away very quickly to the upper quadrant of the phasor diagram, right? And I've dropped my output of the resistor be back at 2 volts. My math is my source voltage, which indicates that, hey, it indicate an open circuit. As I continuously increase that frequency, I'm going to see more and more split and less voltage ready for the resistor, right? And see that massive phase shift in the other direction. Before, my blue line traveled from the left, came right to the middle, and it's getting fuzzy again because, again, look at my amplitude at 98 kilohertz. My amplitude is back to 0.04 volts, very, very small. It cannot compute it, it cannot show you, it's getting very fuzzy, right? So this is a good example of a band pass filter. We started from the low frequency, and as we're increasing the frequency, we saw that the angle, the phase angle, got smaller and smaller, and my output voltage were getting larger and larger to the point that when we're around 6,000 hertz, 6.2 I think, then those two waves, output wave and an input wave, went on top of each other, and then the phase angle between them was 0. Also, the output was showing almost the maximum, indicating the capacitor and inductor reactances were acted like shorts. Okay? All right, so I'll show you that process in a graph as a picture again. Thanks, guys. Now the band stop filters. I have swapped two places between the resistor and the capacitor inductor. Now we're measuring the output across the capacitor inductor, and this is the components I'll be using. I swapped around the component values as well. Inductance, I'll be using 150 millihenry, capacitance of 10 nanofarad, and resistance of 1000, but I didn't change the input voltage, which is 10 volts peak to peak. Same as last time, I'll be starting with the 50 hertz, as you see down here. Input voltage of 9, amplitude of 9. So yeah, and then my math, surprisingly, is not reading anything, guys, right? And what do you guys see this the phase over here? Like 2 degrees, something like that. Okay, like, but it's a millidegree. I didn't know there was such thing as a millidegree, but which means it's 0.9 degree, right? Anyhow, what do you guys see here? You guys see the yellow and you have the math, but how can you have math if you only have like yellow? But it's indicating that I have blue. What's going on there? Do you guys see what's happening here? Well, let me show you some cool thing here. Oh, look at that. I actually had the second channel, which was the output voltage. So which is after the resistor, right? It was the after the resistor is the output voltage. So what does that mean to you? They're completely in phase, that's why. Oops. Oh, I turned that off. Don't do that. Channel 1, boom, as I center it, they're perfectly in phase. What does that mean? It means I'm getting the maximum output. I'm getting the source voltage, right? My input is same as my output. Well, how is it possible? Well, when you have an open circuit after the resistor, because I'm measuring after the resistance, let's look at the schematic again. See, if you're measuring the output after the resistor, and if you're reading high voltage, right, and between the ground, that means my capacitor inductor, that line is completely open. It's only possible when that's possible. Oh, sorry, when it's open, right? Right. So let's start increasing our frequency and see what happens. Right? We know in theory when this band stop filter gets close to the resonant frequency, then we're not going to have any voltage at that moment, and it's going to go back up again to source voltage. So let's see that. As I am increasing the frequency, not much of a difference, right, guys? Still they're on top of each other. Look at my blue. Okay, you're focusing on that. 400 hertz. It's going mad fast. Okay, no change. My phase still 1 degree. 1 kilohertz. Oops. Okay. Oh, maybe it's starting to creep out now. You see that? The blue's trying to come out. Okay, let's go a little faster. And I'll slew the hundreds. Okay. Okay, look at that. Oh, boom. All of a sudden, it came out. From this, it came out. And look at my blue voltage there. My output voltage is significantly getting lower and lower. Significantly getting lower and lower. At that point, right there, look at that. Do you see that? It's, okay, let's get more, accurate. Oh, not 1.9, 1.8. I can't get any lower than that. 1.7. Okay, let's yeah, 1.7, guys. But if you look at the whole graph, right, it's almost flat, right? And then we have the math source minus my output becoming a large number, meaning I'm dropping a good chunk of voltage through the resistor, which means it's only possible when the both inductor and capacitor is acting like short, making the whole circuit a resistive circuit, right? Okay. As I'm going back up, Again, that output is coming closer to my source voltage, and they're aligned perfectly on top of each other again. And the math, obviously, it's not reading anything because there is no, it's essentially zero, right? My source is equal to my output, therefore it's zero, right? You guys all saw that. Let's go find our resonant frequency again. Forget what the number was, but it'll be very obvious as it comes out. Boom, right there, they see the split. And then it's super quick how that happens, right? From nothing happens, and then just over a couple hundred frequency, boom, right? From this to that, right? Right there, right? For about 4 kilohertz, 4.1, 4.2, that's where it is. Okay, that is my resonant frequency, and the line gets flatter because I have no output, because everything has been dissipated across the resistor. There's nothing left, right? And as I go lower, and then it builds back up again very quickly, right? So there it was. There it was. That's our band stop filter. At resonant frequency, you saw that the output voltage just diminished, and the band pass filter, at resonant frequency, we gained a large amount of voltage as an output. So let me show you the same picture, right, in a graph. And that kind of summarizes our demo lesson. Thanks a lot, guys. I'll see you in the next lesson.